Hello and welcome to my new video. Now we are going to do an example. This is number 4 in this series, and you have to watch my previous 2 videos where I explained some things about efficiency, because this example now is referred to the efficiency of a transformer. Now the example says that for the transformer in example 2, so I did previously 3 examples, and it says in example number 2 we have to determine the efficiency at 75% rated output and 0.6 power factor, and for B we have to measure the power output at maximum efficiency and the value of maximum efficiency. At what percent of full load does this maximum efficiency occur? So you can read the example. Now here in this red square I put the most important parameters from the example number 2 here. So we had 2200 volt divided by 220 volt transformer. So from the high voltage is 2200, and the low voltage was 220. The low rated current was 45,5 amperes. The high rated current from the high voltage side was 4,55. It was a 10 kilovolt ampere transformer. The core loss from the no load test was 100 watts, and the equivalent resistance from the high voltage side was 10,4 ohms, and from the low voltage side was 0,104 ohms. So I forgot to put ohm sign or unit here, but you don't have to. I forgot it. So now let's measure the efficiency when we have 75% rated output and 0.6 power factor. Okay, now let's first see what is the formula for the efficiency of a transformer. So here we have the efficiency, Greek letter eta, and now the formula was V2 I2 cosine theta 2 divided by V2 I2 cosine of theta 2 plus the core loss plus the copper loss, which I'm now going to write down IH squared R equivalent H. So this is the copper loss looking from the high voltage side, but it's the same for both situations. Now you can do this from the high voltage side or from the low voltage side. It's not important. If you do it from the low voltage side, then this would be IL squared times R equivalent low. You just use this if you want to use it from the low side, but if you want to use it from the high side, high voltage side, it is this. Now it says that we are taking the efficiency at 75% of the rated output and 0.6 power factor. So how do we calculate it? Well, you know that it is a 10 kilovolt ampere transformer. For example, V2 times I2 therefore is 10 kilovolt ampere. So 220 volts times 45,5, that is 10,000 kilovolt ampere. But it says that we are using 75% of it, so the output power now is because you're using 75% of the load, we are gonna multiply this by 0.75 times V2 is 202 volts, 20 volts, I2, the rated voltage, is 45,5 times the power factor, cosine theta 2 is 0,6. So the rated voltage, the rated current is 100% of the load, 45,5. So then you would multiply by 1. But it says 75% of the full load, so you have to multiply by the 75%, but without the percentage that is 0,75. And the power factor, it says here that it is 0,6. Now, when you calculate that, you get 4,500 watts of power. So this P out is actually this and this in this situation. The core loss is 100 watts. That is from the no load test in example number 2. So this is a parameter that I copied from example number 2. Now we have to measure the copper loss. We can do it from the primary or from the secondary side. We're gonna do it both ways. So it says, so let's see. From the high voltage side, we know that we are using the 75% of the current of the rated voltage. So that is equal to 0.75 times 4.55 squared times the equivalent resistance, but from the high side. Now, if you want, that is equal to, this is also the same as if we were going to use this from the low voltage side. So that is equal to 0.75 times 45,5 squared times, now the equivalent resistance from the low voltage side, which was 0.104. Now you will see that this is the same. I'm just gonna use my calculator and I'm gonna calculate this and this. This is squared times. So you get here that it is equal to 121, comma 1, but I'm not gonna use that. I'm just gonna use 121. So this is from the high voltage side, but you will see that it is same from the low voltage side. So 0.75 times 45,5, I square that, times 0,104, and you get also 121 volts of power. So it's not matter from which side you use it, it's just you have to know what you are doing. Now we have everything. We have the output power on the 75% of the full load. We have the core loss, which usually stays the same if the voltage is a constant, and copper loss, I did it from the high voltage side or the low voltage side, and on the 75% of the load. So this is for the copper loss from the 75% of the load, and its value is 121 watts. So now we can measure the efficiency of the transformer when we have a 75% of the load and a power factor of 0,6. Now the efficiency now. So this here is actually the P out, the output power. This and this is actually 4,500 watts. Plus the core loss, which is equal to 100 watts, plus the copper loss, which is equal to 121. And you get 95. Okay, if you want to multiply with percentage, you just do this, and you get 95,32%. So when you have this situation, now what does this mean for you? So if you put if you have efficiency of this, then you lose 4,68% of power in that transformer when you have this power factor, and then when you have 75% of the full load. Now, that was for A. So this is the efficiency for this situation of this transformer. Now, we want to measure the maximum efficiency. Now, I'm gonna remove this, and we're gonna do this for B. I hope you write all this down in your workbook. I'm just gonna remove it now. If you didn't copy all of it, just pause the video and then copy all of it. And we're now going to do it for B. If you watch my previous video, then you know that the maximum efficiency occurs when the core loss is equal to the copper loss, and if the cosine of theta 2 is equal to 1. So the maximum efficiency of any transformer occurs when we have the core loss same as the copper loss, and we have the cosine theta 2 equal to 1. So when the power is active, so no reactive power at all on the output. Now, okay, so we first have to measure at what percent of the full load will this type of transformer will have the maximum efficiency, or at what percentage. Now we are gonna do this. This is very easy. You know that the copper loss for the same voltage stays usually the same. So that's a rule. So copper loss is 100. Now you get 100. That is equal to, let's say from the high voltage side, IH squared times R equivalent H. So this is the copper loss, looking it from the high voltage side. Now, usually this depends, every resistance of the windings or the conductors stay the same. But let's say you have a good ventilation, you have a constant temperature, and the resistance stays the same. So now IH squared is equal to 100 divided by R equivalent, looking for the high side, is 10,4. Now you get that the current from the high side is equal to square root 100 divided by 10.4. Okay, so that is equal to 3.1 amperes. Let me just take a look. Okay, so when we draw 3.1 amperes, then the maximum 3.1 amperes, then the maximum efficiency occurs. Now we have to know what is the efficiency. And we have to know what is the power output now. Okay, now for example, if IH is 3.1 amperes, then the IL is going to be 10 times more because of the voltage turns ratio. So if you have 10 times on the low side smaller voltage, you will have 10 times higher current. So that is 31 amperes. That's the turns ratio. Now, okay. Now we can calculate what is the efficiency. So this is the value of the maximum efficiency. We still don't know at what load it goes, but we can calculate the output power. And okay, now, oh sorry, I made a mistake. What I was thinking about is what will I multiply this? Well, I'm not gonna multiply it by any number. We can now calculate what is the per unit load. Well, that is easy. Now, that the per unit load, or that X, is equal to IL divided by IL rated. So, when we have 31 amperes divided by the rated low voltage current, low voltage side current, then you get this X. This is you call the per unit loading. About 68.2%. So the maximum efficiency, at what value of maximum efficiency? So that from the 68.2% of the full load will the maximum efficiency occur. So this is the so when you draw this amount of current on the low voltage side, then you have the maximum efficiency. And let's see what that efficiency is. Now, we're not gonna say, well, this is 0.682 times V2 I2. We can just put, instead of I2, IL. But if you use 45,5, then you have to use here 0.682. Now, we're just gonna write like this. V2 is 220 times I2. Now I'm going to use this 31 ampere. And cosine theta 2 is equal to 1. That is for the maximum efficiency. Now, this and this is the same. Just rewrite this. I'm not going to multiply by 1. Now, the core loss is 100 and the copper loss is also 100. And when you calculate all this, you get that the maximum efficiency is, let me just see, 97.15% of, yeah, so the maximum efficiency of the transformer, if you bring these voltages, is going to be 97.15%. So in real life it's almost impossible to have this much efficiency. I mean, it is possible, but it is almost impossible to have an ideal situation that cosine theta 2 is 1 and the core loss is equal to the copper loss. But now you see at what situation you have the maximum efficiency of a transformer. And in this particular transformer, the 97.15% is the maximum efficiency. Okay, now thanks for watching, and I hope you learned something, and see you in my next video.